2 days ago, an object older than our solar system passed through the outer edge of Jupiter's gravitational domain and continued on its way out of the solar system. There was no emergency broadcast, no globally coordinated announcement, no sudden shift in public attention. Yet, for those following the data, the event marked one of the most unusual encounters ever recorded between an interstellar object and a planetary system. The object, designated 3I Atlas, is only the third confirmed visitor from beyond our solar system ever observed. Unlike its predecessors, however, it has become the subject of growing scientific interest, not because of any single extraordinary property, but because of how many unusual characteristics appear together in one place at one time. Initial attention focused on its trajectory and origin. Unlike comets that orbit the Sun, 3I Atlas arrived on a hyperbolic path, confirming that it was not gravitationally bound to our system. It came from interstellar space, moving at tremendous speed, passing through the inner solar system, and now heading outward again. That alone places it in rare company, but what elevated interest further was the emerging evidence about its age. Observations using the James Webb Space Telescope provided isotopic measurements suggesting that this object may have formed between 10 and 12 billion years ago, in a universe approximately 13.8 billion years old. That places its origin in a period when the Milky Way itself was still young, long before the Sun or the planets had formed. Age, in this context, is not just a number but a record of environment. The early Milky Way was markedly different from the galaxy we observe today. It contained fewer heavy elements, which astronomers refer to as metals, and was dominated by simpler atomic compositions. The isotopic signatures detected in 3I Atlas appear to reflect those early conditions. Elevated levels of deuterium and unusual carbon ratios point toward formation in extremely cold, metal-poor regions, conditions consistent with early star-forming environments. Such measurements function as a kind of chemical fingerprint, allowing scientists to reconstruct where and when an object likely originated. In this case, the data suggests that 3I Atlas is not merely an interstellar traveler, but a preserved remnant of a much earlier epoch in galactic history. The implications of this are significant. If 3I Atlas formed in the early galaxy, it would have spent billions of years drifting through interstellar space before entering our solar system. During that time, it would have been exposed to cosmic radiation, gravitational perturbations, and the sparse but persistent influences of the interstellar medium. Objects that survive such conditions can act as time capsules, preserving chemical information from eras otherwise inaccessible to direct observation. This has led researchers to propose that 3I Atlas may belong to a broader population of ancient planetesimals, building blocks of planets, that were ejected from their original systems during chaotic phases of planetary formation. If so, then objects like this may be far more common than previously thought, even if detecting them remains difficult. As it moved away from the Sun after perihelion, 3I Atlas passed through a region of space occupied by an active spacecraft, the Jupiter Icy Moons Explorer, or JUICE, operated by the European Space Agency. This coincidence provided a rare opportunity. Unlike ground-based telescopes, which observe from great distances, a spacecraft in transit can potentially capture higher resolution data and measure environmental conditions directly. JUICE's onboard instruments include cameras, spectrometers, particle detectors, and magnetometers, tools capable of analyzing both visible structure and invisible physical processes. The mission released imagery showing the object's coma and tail, confirming its comet-like appearance. However, much of the detailed instrument data, particularly measurements of particle interactions and electromagnetic signatures, has not yet been fully described in public scientific literature. This is not unusual in itself. Mission data often undergoes careful calibration and analysis before publication. Still, the presence of such data adds another layer of anticipation to ongoing research. The timing of the encounter with Jupiter has also drawn attention. On March 16, 2026, 3I Atlas passed at a distance of approximately 53.6 million kilometers from the planet. This distance places it near the boundary of Jupiter's Hill sphere, the region within which the planet's gravity dominates over that of the Sun. Passing through this region without being captured is not unprecedented, but it is relatively uncommon. What makes the event noteworthy is the geometry of the trajectory. As the object moved outward, it experienced a measurable gravitational influence from Jupiter, effectively altering its velocity. In orbital mechanics, such interactions are well understood and frequently used by spacecraft in the form of gravity assists. These maneuvers allow a spacecraft to gain speed by borrowing energy from a planet's motion. In the case of 3I Atlas, the interaction appears consistent with a natural gravitational slingshot. The object entered the outer region of Jupiter's gravitational influence, was accelerated, and then continued on its outbound path at an increased velocity. It is now moving away from the Sun at over 60 kilometers per second. While this behavior can be explained through established physics, it adds to the overall picture of an object whose journey through the solar system involved a sequence of precisely timed and dynamically significant events. Another area of study has been the object's motion itself. During its passage through the inner solar system, researchers detected non-gravitational accelerations, small deviations from the path predicted by gravity alone. Such effects are commonly observed in comets and are typically attributed to outgassing, where jets of vaporizing material produce thrust. However, modeling these effects for 3I Atlas has proven complex. The observed accelerations do not align perfectly with simple outgassing scenarios, suggesting that additional factors may be involved. These could include asymmetric jet activity, variations in surface composition, or structural properties that influence how material is released. Importantly, while the deviations are unusual, they remain within the range of phenomena that can be explored through natural explanations. Chemical observations have added further depth to the investigation. Spectroscopic studies of the object's coma have revealed the presence of various compounds, including complex carbon-based molecules. Some measurements have indicated unusual ratios of elements such as nickel and iron, prompting discussion about how such compositions could arise. In early, metal-poor environments, heavy elements are less abundant, making certain observed ratios more difficult to reconcile with standard formation models. However, astrophysical processes are diverse, and localized variations in composition are possible. Collisions, thermal processing, and long-term exposure to radiation can all alter the makeup of a body over time. As a result, while the chemical profile of 3I Atlas is intriguing, it does not yet point to a single definitive interpretation. One of the more compelling aspects of the object is the apparent preservation of complex molecules over extremely long timescales. Organic compounds detected in the coma suggest that at least some material remained shielded from destructive cosmic radiation for billions of years. This implies the existence of protective layers, ice, dust, or rock, sufficient to insulate interior regions. Such structures are consistent with models of cometary nuclei, which often contain stratified layers formed during accretion and subsequent evolution. The release of these materials after perihelion, as solar heating increases, is also consistent with known comet behavior. The combination of extreme age and apparent preservation raises interesting questions about the durability of such materials under interstellar conditions. As the object continues its journey outward, it is undergoing visible changes. The coma that once surrounded it is diminishing as temperatures drop and volatile materials cease to sublimate. Its brightness is fading, making it increasingly difficult to observe with telescopes. This transition marks the end of the most active phase of its passage through the solar system. Soon, it will become a faint, inert body once again, indistinguishable from countless other objects drifting through interstellar space. Meanwhile, discussions within the scientific community have turned to the possibility of intercepting such objects in the future. Conceptual studies have explored the feasibility of missions designed to rendezvous with interstellar visitors using advanced propulsion methods such as solar sails. These missions would be challenging, requiring rapid response times and precise trajectory planning. In the case of 3I Atlas, the window for such an attempt is extremely narrow and is closing rapidly as the object recedes. While no mission has been publicly confirmed, the existence of these studies reflects a growing recognition of the scientific value of direct exploration. Throughout this process, it is important to distinguish between observation and interpretation. The data collected so far presents a complex but not incomprehensible picture. Each anomaly, whether related to age, composition, motion, or trajectory, can be approached within the framework of known physics and chemistry. The challenge lies in integrating these elements into a coherent model that accounts for all observations simultaneously. This is a familiar process in science, where initial surprises often give way to deeper understanding as more data becomes available. At the same time, the rarity of such objects ensures that each new detection carries disproportionate importance. With only a handful of confirmed interstellar visitors, there is limited opportunity for comparison. Each one expands the dataset, refining our understanding of how planetary systems form, evolve, and interact with the broader galaxy. In this sense, 3I Atlas is not just an isolated curiosity, but part of a developing field of study that connects our solar system to the wider cosmic environment. As it departs, the object leaves behind a trail not of material, but of information. Observatories continue to analyze the data collected during its passage, and scientific papers will continue to emerge in the months and years ahead. By the time the full picture is assembled, 3I Atlas will be far beyond the reach of any instrument we currently possess. It will return to the vast, cold expanse between the stars, carrying with it whatever secrets remain unresolved. What remains is the record of its brief encounter with our solar system. An object formed in the early history of the galaxy entered our observational reach, interacted with our sun and planets, and provided a glimpse into conditions that existed billions of years before Earth formed. Whether ultimately classified as an unusual comet, an ancient planetesimal, or something that challenges existing categories, 3I Atlas represents a rare intersection of timing, technology, and discovery. It arrived at a moment when humanity had developed the tools to detect and analyze it, and it departed just as quickly, leaving behind questions that will continue to shape our understanding of the cosmos.